high-TC superconductor, and then there are many studies. It's just this study is triggers many study, and we need to develop. And okay, this method is today. I'm just showed the how to grow these films and also the electric treatment of the visco crystals. Okay, the first part is just I will show the how to grow, and but I will give you the brief introduction about the terahertz. We can just tune the carrier concentration of visco on the by applying the current. And now the terahertz is just lies between the microwave and infrared region, and it's very useful for these application areas. And what people doing just semiconductor, you can gap, and we have a platform, and we are here in this competition, okay, and we can just grow. We can make some. Oops. Can we go further? By the voltage between the two, kind of the phenomena is just proved by the experimental study from the 1960s, and they just increase the power and frequency of this. They just use the conventional Josephson junction. Actually, how they increase the associated with the superconducting gap. You can see the crystal structure of this high TC, and superconducting copper oxide layer separated by the strontium and bismuth oxide layer. This is the alternating stack and along the z-axis. They are natural stack, and this allows the loss the propagation of the Josephson wave plasma waves, and they have the really large energy gap and then we can get to the terahertz emission up to the 13 terahertz. Now this is the argon group, how to just discover the powerful terahertz emission. You can see the mesostructure, and they apply just bias this large mesostructure, and they apply the terahertz emission. You can see the signal and after the bolometer, silicon bolometer, and during this IV curve of this meso. Okay, next one is actually these are just the how to the principle of the terahertz emission. If this Josephson plasma frequency just match the cavity resonance, and then we can get to the terahertz emission. Okay, now my colleague increased the power of this terahertz emission 0.6 milliwatt. And another one is that we can just use this platform as like a filter, terahertz filter, and also we can use this platform as a detector. Okay, you can see this, and sharper step of the IV curve of this junction when we irradiate by the terahertz emission. Okay, and we can just generate a terahertz emission, or we can detect the terahertz emission by using this platform. And why not to make some the terahertz on a chip structure? What we need a really large, uniform, thick, and good quality of visco structure. And you can see here is the famous superconducting of this component, and there is a 20. These are the low TC phase. TC is 20 Kelvin. These are just the bismuth 2212, and this is the high TC phase. Especially we concentrate to grow this one, and there are many methods, and I will not go to detail, but they are deposition rate very low, and also they are very expensive. The best method is molecular beam epitaxy, but it has a really low deposition rate. They are very cheap. And we choose the liquid phase epitaxy because this liquid phase epitaxy is just the visco is just dissolved in the potassium chloride solution easily, and then we have the mobility. Then we can just obtain the thin film structure on this substrate here. Okay, there are many parameters if you are using. These are the disadvantage of the liquid phase epitaxy. If you change some of the parameter, for example, growth temperature or temperature gradient, or this atomic ratio or depth of this substrate, then then you can get some deviation in your structure, and especially maybe you cannot get any thin film. Especially temperature gradient is very important. This visco is dissolved and then driven by the temperature gradient here from the bottom to up. And these are just some features, and after calcination, and we put the potassium chloride, we treat and quench this structure, and then these are after growth experiment. And you have to be careful if you choose this kind of the method. You have to just select the true materials. These are just the corrosion on the platinum rhodium. Rhodium, we found the rhodium inside. Also, we used the NGO substrate, and we found gallium inside our structure. And the best one is the MgO substrate. Okay, this is the just reason why we need the platinum material. Yeah, these are just the structure we established in at Sunum, and you can see here the structure is just this one is moving, and this part also moving, and then we can control. These are the control units. Let me just let's take the ulcer technique to prepare this furnace. And yeah, we are still working on to describe the temperature gradient and which ideal conditions. And you can see here the console simulation of our furnace, and we are still working on it. And I will not go detail. These are the first films we obtained. You can see it's very nice area. It's like a mirror-like, and we have also really large grains. Then we can fabricate our sample. XRD, but then XRD just shows some of the foreign phases in our structure. We are still working, and these are just the same structure we established at the Argonne National Lab. And yeah, we found really nice. We optimized the LP system very well, and now that we just obtained the nice film is 870 Celsius, and then we have the temperature gradient is 3 centigrade per centimeter. Okay, now these are just you can see the 4 XRD result of the 4 sequential growth films, and they are really sharp. And we really the bismuth 2-1-2 phase, and XRD EDX result shows the same thing. Only one is if you keep in this ops. Okay, can we go back? Oh, I can do it. Okay, here. Okay, and only thing is we have to be careful if some structure can stay because they form the really large molecules and stays at the bottom, and then our structural concentration in these elements is getting decreased. These are just magnetization measurement, and we have so this effect below the 250 Kelvin, it's persistent, but above the 250 Kelvin, the doping effect. But we have these or electric field effect or just electron immigration effect. This one is very destructive, especially this one. But if you change any oxygen, then this effect is reversible, also persistent. And if you apply an electric field, then when you just take off the electric field, and then maybe you will lose the doping effect. Our doping effect is persistent. And these are just, we also tried another peroxide later visco. And then you need this kind of double crossbar crystal structure. I spent a lot of time to optimize this parameter by lithography. Then I fabricate the sample on these underdoped crystals. We start here. You can see the IV curve here. Yeah, here. And then we start here, and we increase the T by current injection. And then you can see the IV curve is getting and going increases also. And here still the superconducting transition is very large, and our current is growing, changing by JC, and we just looked at the logarithmic scale of the JC. TC just showed this parabolic curve. This resembles, and these are just the fit formula here. This one resembles the empirical correlation. You know this correlation, and when you change the oxygen of this one, this is very similar. Then we can just calculate the whole concentration. Okay, and now we have another formula how the hump structure or some, and also we also looked at this RT curve of this one, and we just obtained this onset of the pseudo gap. It's just directed to the section of the IV curve. It's just some point which called this is the sources, and without any doing some chemical change or something. Okay, these are the end of my summary, and this BISCO is very nice platform to do some of the terahertz, especially terahertz devices, and how to go further, and we can just grow the large structures, large BISCO films. If films is the high quality, then we can combine all of the terahertz devices. Then we can realize the terahertz chip. And also we can use this current injection, and we can just manipulate or just tune our carrier concentration to change the frequency of the terahertz emission from this source. Yeah, we also tried this current injection in some metal oxide, try to develop the new terahertz sources. And also we are just looking for some of the conventional Josephson junction, if they can emit the terahertz or not. Thank you. These are our cryostat, and these are just the dry dilution refrigerator. And we can apply the 12 Tesla and by using this. And another one is this facility is just, we can just look the angular magnetic resistance using this dipstick. Thank you very much.